It is given that A is a 2 by 2 matrix and we have to check which of the statements is correct. Now it's a direct straightforward question. It's a property, one of the properties of determinant. Determinant A is nothing but trace of A whole square minus trace of A square divided by 2 will be the determinant for a 2 by 2 matrix. So the answer is option A. D square minus 2D plus 5 times of y is equals to 0. Its auxiliary equation is m square minus 2m plus 5 is equals to 0. That implies m is equals to 1 plus or minus 2i, or it can be written as d is equals to 1 plus or minus 2i. Now for the given differential, that is d square minus 2d plus 5 whole square, there will be obviously repeated roots. Hence the equation, that means the solution will be y is equals to e power x into c1 cos 2x plus c2 sin 2x plus x into e power x of c3 cos 2x plus c4 sin 2x, which is nothing but option C. Given function is z is equals to x minus 1 whole square plus 2y square. We have to check whether the function attains maximum point, minimum point, or neither minimum nor maximum, which is saddle point. In order to check this, let us see some property. fxx fyy minus fxy whole square. If this is greater than 0 and also if fxx and fyy are both positive, if all of them are positive, then any function will attain minimum. Now here xx is nothing but differentiating f partially with respect to x twice. So fxx will be here. In this case we have to take zxx. So zxx is nothing but 2 times of x minus 1 is zx, and if you further differentiate it will be 2. Similarly zyy will be, if I differentiate once it is 4y, if I differentiate twice it will be 4, and fxy, that means zxy is nothing but, first we'll differentiate it x times, with respect to x, which is 2 times of this, and if you differentiate the function by y it will be 0. Now let us substitute here fxx into fyy, that is zxx into zyy, 2 into 4 minus 0, which is always greater than 0, and also fxx, zxx and zyy are positive. So this function will attain a minimum value. Option method, we have to find the first approximation of the equation x cube is equals to 3, and also given x naught as 1. Now we know that x1 is nothing but x naught minus f dash of x naught by f of x naught by f dash of x naught. Now we know what is f of x. F of x is nothing but x cube minus 3. So f dash of x will be 3x square, and x1 will be x naught. X naught is nothing but 0 here, minus what will be f of x naught? X naught cube minus 3 by f dash of x naught will be 3 times of x naught square. If we substitute the values, that is x naught is given as 1, this is not 0, so 1 minus 3 by 3 times of 1. This is nothing but 1 minus of 2 by 3, which is equals to 1 plus 2 by 3, which is 1 plus 0.666, so on, which is equals to 1 plus 0.67, which is 1.67. So the answer is option A. Value of the integral whose boundaries are enclosed by the region y is equal to root x and y is equals to x square. Now m is given as 3x square minus 8y square, and n is given as 4y minus 6xy, and dou m by dou y is nothing but minus 16y, and dou n by dou x is nothing but minus 6y. So we can use Green's theorem here to solve. Integral over c m dx plus n dy can be written as double integral over r dou n by dou x minus dou m by dou y dx into dy times. Here the value of x, if we solve these equations, value of x will be from 0 to 1, and the value of y will be from root x to x square, and dou n by dou x minus dou m by dou y is nothing but minus 6y plus 16y times of dy dx. This can be written as 10 times of integral x is equals to 0 to 1 and y is equals to root x to x square y of dx dy, and if we integrate it will be x is equals to 0 to 1, 10 is out, y square by 2 times of y is equals to root x to x square, and this can be written as 5 times of x square by 2 minus x power 5 by 5 after integrating twice over the limit 0 and 1, which is equals to 5 times of half minus 1 by 5. If you simplify, it is 3 by 2. But his answer is C, A.
Equations of the Boolean variables xyz have the following solutions for xyz respectively. Here xy should be 0. It is possible if x or y should not be 1, means x can take either 0 1 or y can take x as 0, but both cannot take 1 simultaneously. So and xz must be 1, then only this equation is satisfied. Again this must be 0, means here xy is 0, means 0 plus z bar should be 0, means z should be 1. So either it is 1 0 1, because here x is 1, so y should be 0, so xyz should be B. Option B is correct. 4-bit full adder is shown in the diagram, as well as the B0 is passed to the exclusive OR gate, as well as 4-bit data, that is A0, A1, A2, A3, and B0, B1, B2, B3, that is given to the 4-bit full adder, and the data B is passed to the exclusive OR gate. We have to find out what kind of results this network leads to. So if we take basic XOR function, that is, this is x, suppose assume x, this is 1, this is output y is equals to x bar 1 plus x 1 bar, so it leads to x bar, means y equals to x bar, means exclusive operation is performing if Cn is equals to 1 here, so then the output of all the exclusive OR gates are inverted, means it is kind of a ones complement form. Then we are adding carry 1, that is A3, A2, A1, A0, ones complement B data bits, and then we are adding 1, means it is kind of a 2's complement of the B data, and then we are adding it to the A's data, means it is kind of an output is nothing but A minus B. So it is a 4-bit binary subtractor, that is option D is correct. The output of the following logic circuit is, see, before we deciding what kind of logic it is performing, we have to write the truth table for this particular figure. So then only we can decide what kind of logic function it is performing. So S0, this is S1, this is output equation. S0 is always 0, S1 0, S1 is 1. If S1 and S both are 0, output is X. If S1 is 1, output is 1. So see here X, Y, 0 0 0 1 1 0 1 1. So if 0 0, so this is the truth table for the block diagram which is shown in the figure for the 4 by 1 mux. This is 4 by 1 mux. So output equation is nothing but X plus Y, that is, it is performing an OR gate operation, that is option A is correct.